whether the function is convex or concave. Therefore, I always describe the task finding maximum or minimum. So now we needed a product rule. In the previous example, we only needed the power rule, but now we do the product rule. But luckily, it's quite simple because we have a logarithm and we have x, so the derivatives of both of them separately, they are quite simple. So we got logarithm of x plus 1 for a derivative, and then we equate this to 0, which effectively means, it means that logarithm of x is equal to minus 1. And here we needed to remember the usual trick, how to get rid of the logarithm. And the trick is that if the left-hand side, in terms of logarithm, is equal to right-hand side, then if I use them as powers of some other function, then equality in the middle should be preserved. But if I choose this function to be e, if I choose it to be the exponential, then e and logarithm, they cancel each other. And then we only have x on the left-hand side. So we get that x is equal to e to the minus 1. Then we took a second derivative of logarithm of x plus 1. And that was very easy because logarithm of x has a derivative of 1 over x. And the derivative of 1 is equal to 0, but we never write 0. And then what we did, we now wanted to do the test, right? So we substituted or we inserted the critical point to find out whether the second derivative is positive or negative, meaning whether the function around the critical point is convex or concave. So when we insert e to the minus 1, we have 1 over e to the minus 1, which is just the same as e. And e is positive because e is approximately 2.7 and many more numbers. So it's strictly positive number. So the function is convex. Okay, so meaning that e to the minus 1, or x equals e to the minus 1, is a location. It's a location of local minimum. Local minimum. Okay, so what we can do now, we can just insert. We can just insert the value. We can just take this number, e to the minus 1, and we can find the minimum. So if I do a function at e minus 1, so I have e to the minus 1 times logarithm of e to the minus 1. So I just substituted, instead of x, I substituted e to the minus 1. Here we cannot do anything. E to the minus 1 is e to the minus 1. But here we can do something. So I can simplify this expression quite a bit. So if I have e to the minus 1 inside of the logarithm, what can I do with minus 1? Right? I can take minus 1 and I can move it downstairs. I can just move it like that. So I have e to the minus 1 times minus 1, and logarithm of e remains. However, what is logarithm of e? So what is logarithm of e? It's just 1, right? So here we go. So therefore, it's e minus e to the minus 1. So this is our minimum value of this function. All right, and I sketched it, so it looks like this. It looks like this. So this is f of x equals x logarithm of x. And then in here we have a minimum. Somewhere here we have e to the minus 1, and this produces minus e to the minus 1. We also see that this turns out to be also a global minimum. So we declared it to be local minimum, but actually it happens to be global minimum as well. It happens to be global minimum. So this is local minimum, but also a global minimum. And the reason for this is, well, we need to think about it a little bit. Let's just spend 1 minute before we go to another very important exercise. First of all, why does this graph look like this? So why don't we consider negative values here? Judging by this. Right? We cannot have negative values because logarithm is undefined on negative values. Okay? Fine. So it means that we are considering only positive values of x. And if we look at second derivative is 1 over x. And if x is only positive, does that mean that second derivative is always positive? So it means that second derivative is always positive. And therefore, this function is strictly convex, actually. So let's write this down. That second derivative is 1 over x, and 1 over x is strictly positive for strictly positive x values. Because that's what we consider. And we consider this because of logarithm. Because of logarithm of x. This means that the function is strictly convex. And therefore this happens to be the global minimum. That the function is strictly convex. Right. So if we consider all the permissible x values, all the positive values, second derivative is always positive. And in this case, since it never becomes concave again, it means that it has one unique bottom point here. And we were able to find it by the use of derivatives. All right, so this was, again, a very important example, I believe, because it also required us to think why it happens so, that this is also a global minimum. Okay, so now let's go to something that I called a function analysis. And here we're going to do similar steps, similar exercises. But the exercise is this. So let's say I'm going to give you a function. So I'm going to give you a function, f of x equals x to the power of 3 minus 2x to the power of 2 minus 3x. And let's say my question is this. Sketch the graph. sketch the graph. And we can proceed in various ways. Right? So we can proceed, and we can just make a little table, and we can start plugging in different values of x and y, and then start sketching on x and y axis. But this is a bit cumbersome, and it's a bit random. So you just pick random points, and you just start putting them on the table. But we can have much deeper understanding that would allow us to sketch the graph of any function if we do the derivatives, and if we understand where the function is increasing, decreasing, where it's convex, where it's concave, then it's very easy to take this information and put it on the graph. So I put this in the note in the week's file, but this is the usual steps. So if you were to draw a graph of, let's say, somewhat complicated function, these would be the usual steps that give nice information. Find where the function is equal to 0, the function itself, where the graph of the function hits x-axis, where it's equal to 0. Find where the function is positive, where negative. Okay. Find the derivative of that function and determine the following. So where the function is increasing by finding where derivative is greater than 0, and where the function is decreasing. So we find where derivative is negative. And of course, where the function's derivative is equal to 0, then the function is neither increasing nor decreasing. You have a critical point where you potentially have local minimum or maximum. And then you compute the second derivative, and then you can determine whether these are indeed minimum or local minimum or maximum points, and we can find where the function is increasing, where the function is decreasing. There's this one little thing, find an inflection point. I'll explain in a second what that is. And then, yes, use the second derivative to understand where the function is convex, where the function is concave. So it's going to give you a lot of information about how the function should look like, where it's increasing, where it's decreasing, where it's positive, negative, and then it's quite easy to take that information and implement it on the graph. Just before we proceed, there is this word, point of inflection. So point of inflection is where the second derivative is equal to 0. Right? We so far didn't have this. So we only looked where second derivative is positive, convex, second derivative is negative, concave, and where second derivative is 0, that's exactly the point where it's a turning point, where the function turns from convex to concave or vice versa. So I'm going to write it right here. That inflection point is where the function turns from convex to concave or vice versa. So it changes its properties. Or vice versa. All right. So these are the 4 steps. So we have about half an hour. We have a function. Let's try implementing these steps. So to find as much information about this function as we can, and then let's use that information to sketch the graph of this function. When you look at this function, it's not very obvious how it should look like. So it has a power of 3, so it should be something like this, but it's not entirely clear. But let's try to find information through these steps, and then we can maybe say way more and be way more precise. So let's do it slowly and surely. If we don't finish, I'm going to finish this in my office, and of course I will upload in the lecture notes, and then we will look at it again in the next lecture. I think we can finish. So the first step, right? Try finding where the function is equal to 0, where the function itself is positive, where the function itself is negative. So I'm not talking about derivative, I'm talking about the function itself. So I gave you a function, and my function is this: f of x equals x to the power of 3 minus 2x to the power of 2 minus 3x. And first, let's equate it to 0. So I want to solve this. Where is this equal to 0? So where the graph of this function hits the 0. So we haven't solved equations where we have power of 3, right? So we know the formula for equations to the power of 2. Very nice formulas to find solutions. But here we can notice that we can factor out x. So if I factor out x, I have x to the power of 2 minus 2x minus 3 in the brackets. Okay, so if you factor out x, it becomes way clearer what's going on here. We have only two cases. We have two things that can happen. X is equal to 0, or all of this is equal to 0. And we know how to equate x squared minus 2x minus 3 to 0. So this now we know how to solve. That's reduced to quadratic equation. So two situations: either x is equal to 0, then the whole thing is equal to 0, or that quadratic expression is equal to 0. But this we can solve. That's not a problem. So again, we can just use the formula. X1 is equal to minus b. So minus b is minus 2 times minus 1. So that's 2 plus square root b squared minus 2 squared, it's 4, minus 4 times a times c. A here is 1 implicitly, c is minus 3. So times 1 times minus 3. And then I'm going to divide by 2a, which is 2 times 1 equals to 2. Okay, so I have 2 plus square root. Again, I have two minuses, minus and minus, which makes it a plus. So 4 plus 12, that is 16. And I'm going to divide it by 2. Right, so I have 2 plus 4 over 2, and that is equal to 3. So 6 over 2 equals to 3. And I don't want to go to the new page. Let me write x2 right here, which is basically just 2 minus square root of 16 over 2, which is equal to 2 minus 4 over 2, and that is equal to minus 1. Minus 2 over 2, minus 1. Okay, so now we have it. We know that the function itself is equal to 0, at 3, at 1. So we already found it. Okay, so we have 3 points, and it hits 0 in these 3 points. Perfect. Now, I want to understand where the function is positive and where it's negative. Where it's negative. So here, it's extremely convenient to use sign diagram. We can do a very quick sign diagram. So, for example, I already know that my function is x to the power of 3 minus 2x to the power of 2 minus 3x. I factored out x, which left me with x squared minus 2x minus 3. But what we did in the previous step, we solved where this polynomial of second degree is equal to 0, right? Which means I can use minus 1 and 3 to factorize this part. So I can factorize this part immediately. So, because we already have the roots of this polynomial, we can factorize it. Which means that I have x minus 3 and I have x plus 1. Right? So here I'm using factorization formula. A, x minus x1, x minus x2. So I'm using factorization formula, and in our case, x1 was 3, x2 was minus 1. So therefore, I plugged in this one here, and I plugged in minus 1. And minus turned into plus. Okay, so now I have this very nicely factorized, meaning that now it's straightforward to implement sign diagram. I know where this whole function is equal to 0. It's equal to 0 at 3 points. It's equal to 0 at minus 1, it's equal to 0 at 0, and it's equal to 0 at 3. Right? And I have the following components. So I have x, I have x minus 3, I have x plus 1, and then I have all of it together. X, x minus 3, x plus 1. So here I can make a little table where I'm going to write down the signs. So we're just going to plug in some values. And then we're going to read off the answers. Okay, so now if I insert, instead of x, anything from minus infinity to minus 1, well, this is just negative. If I insert anything from minus 1 to 0, clearly this is negative. And if I insert, instead of x, anything from 0 to 3, well, this is going to be positive. And then, of course, anything from 3 and above, instead of x, is going to be positive. Now I will do the same for this guy, x minus 3. So if I take any negative number from minus infinity until minus 1, and if I insert in here, so minus 2, minus 5, I hope it's clear that this is negative, because I'm subtracting 3 on top. Same in here. If I insert anything from minus 1 to 0, let's say minus 0.5 or minus 0.1, something negative but small, close to 0, then this is still going to be negative. Okay. Now I go here. If I insert anything from 0 to 3, let's say 1, still negative. So a lot of negatives here. So let's say 2, 1, and if I subtract 3, this is negative. And now clearly, if I go for anything beyond 3, and if I subtract 3 from that number, this is going to be positive. And then the last one that I should examine is this one, right? So now I need to plug in a negative number from minus infinity to minus 1. So, I don't know, minus 2. And if I insert here, this is going to be negative. Now, if I insert something between minus 1 and 0, so let's say minus 0.5, and if I add 1 to that number, because here I'm adding 1, then this is going to be plus. And now it's very clear. If I insert anything bigger than 0 or anything bigger than 3, this is going to be positive. this is going to be positive. Okay, so we are now done. All we need to do is to collect the signs. So if I have negative and negative, I have plus. And if I have negative again, I have minus. So here, minus. If I have minus and minus, so minus times minus, it's a plus. And if I do plus again, then I have plus. Now I have plus and minus, so that's minus. And I have plus again, negative and plus, that's minus. And now I have all the pluses. So plus, 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 3 times plus, or plus times plus, times plus, times plus. So we found a lot of new information. I know that this complicated function is increasing from minus 1 to 0 and from 3 to plus infinity. But I know that, sorry, not increasing, it's positive. It's positive from minus 1 to 0 and from 3 to plus infinity. And now that it's negative from minus infinity to minus 1 and from 0 to 3. So this is very important. So we can write this down to ourselves. So we can write down that function is positive for x in minus 1, 0, and 3 plus infinity. Right? So this is where it's positive, and it's negative from x in minus infinity, minus 1, and 0 and 3. So in these intervals, the function is positive, and in these intervals, it's negative. At these corners, it's actually equal to 0. But I mean, we can include them, we can exclude them. They are not outside of domain, so we are not dividing by 0 or anything. So it doesn't really matter. We can write that we exclude, but we can include as well. It's not a mistake to just do it like that. Okay, so we know where the function is equal to 0, where it's positive, where it's negative. Now, in the second step, we need to find where the function is increasing, decreasing, or where it has critical points. So we need to find where the derivative is positive, meaning the function is increasing, where the derivative is negative, meaning the function is decreasing, and we need to find where the first derivative is equal to 0, meaning stationary point, or points. Stationary points. That's what we need to do now. So now we need to take a derivative of this function. So I'm just reminding you that originally the function looked like x to the power of 3 minus 2x to the power of 2 minus 3 times x. So that's how the function looked like originally. And clearly, to answer these three, we need to take a derivative of this. So can you tell me what the derivative of this is? What's the first? 3x squared, nice. Then minus 4x and minus 3. Yeah, so, I mean, the derivative is not complicated, it's just power rule, and we can just take them separately and then combine together at the end. And now we need to solve where this is equal to 0. We need to solve where this is equal to 0. Okay. So let me go to new page. I need 3x squared minus 4x minus 3 equals to 0. Okay? So I need x1, so minus b, that is going to be 4, right? Minus b, minus 4 times 1, plus square root 16